Okay, now we are going to study that how could we solve recurrence relations. Solving recurrence relations could sometimes be quite challenging. There are three methods which are used to solve recurrence relations. The first one is recurrence trees. The second one is called substitution method, and the third one is called master's method. And we will see all three of them one by one. Amongst the three, the one which I am going to take up first of all is recurrence tree method. So let me start with recurrence tree method. Okay, here I have written down, this is not a complete algorithm, you can say it's partially like an algorithm. What I basically want to say with this thing I have written down over here is that there is an algorithm of size, of input size n, an algorithm taking an input of size n. Now here are some steps, and this is making a call to the same algorithm A on an input size of n by 2 or input size of n by 2, that half the original input size. This is the input size and it is making a call to the same algorithm on a size n by 2, and it is making that call twice. So each of this, when n by 2 will be called and it is executing, because this is like a recursive algorithm. When n by 2 will be called, it will make a call to an by 4, because this is executing and it will make a call to an input size which is half of its input size, half of this input size. So an by 4, and this call will be made twice. So an by 4, this will also make two calls to an by 4, n by 4 and same algorithm on size n by 4. Now each of these this call, each of these, when they will be executing, when this will be executing, it will make two calls to the same algorithm A on the size half of this size. That means this will be making two calls to algorithm A on input of size n by 8. The same will happen with all of these. So first of all, let me write down the recurrence equation for recurrence relation for this. So the recurrence relation will be T of n, that means the time taken by the algorithm on input of size n, will be equal to twice into T of n by 2, because the same algorithm on size n by 2 is being called twice, plus I am assuming over here that these steps is taking c into n times. So plus c into n. Okay, and I'll also say that T1 will be equal to 1. Okay, so when n is less than or equal to 1, return 1. I'll assume that okay, T1 be equal to 1. You can also say c, but okay, c we can call c as theta of, we can write c as theta of n. It's the same thing. Here also c into n. Okay, so I am going to solve this recurrence equation using recurrence tree method. So let me, I am rubbing this so that I could make some space on the board. So, okay, so now initially we have this time taken by the algorithm on input size of n. It is divided into two parts. By divided I means two calls are being made. Two calls are being made. One call is being made on size n by 2. Another call, this is also being made on size n by 2. So it is making two calls on the same algorithm of the input size here is n by 2 and the input size here is n by 2, and this will take c into n times this recurrence relation I have written over here. I have written the same thing over here in as a tree, in the form of a tree. So time taken by the algorithm of on an input of size n is c of c into n plus the time taken by the algorithm on input of size n by 2 and input of size n by 2. Okay. Now this could be written as, will follow the same format, right? Half the size over here and half the size over here. So Tn by 4, 2 calls will be made to the same algorithm on half the input size, half of this current input size, half of this n by 2, so it is n by 4 and n by 4. This will take time n by 2 C into n by 2. Here also same thing will happen. This will be Tn by 4, Tn by 4, and this will be C into n by 2. So we have C into n by 2 over here and we have C into n by 2 over here, and the C into n by 2 is occurring twice at this level of the tree. At this particular level of the tree, C into n by 2 is occurring twice. So to make our task a little simpler, what I could do, I could write it like this: Cn into 2. I could write it like this. So what is this will become? This will become C into n. Okay, clear? That which I have done over here and over here and over here, the same thing I will repeat again. So okay, let me draw one more level for you. What will happen? We will have Tn by 8, Tn by 8. This will also have Tn by 8, T. Time taken on size n by 8, 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 time taken on size n by 8. So each of this call on size of n by 4 will make 2 calls to size n by 8, and this will take time C into n by 4. This will also take time C into n by 4. So C into n by 4 plus 2 calls, the time taken by this is C into n by 4 plus time taken by a call on n by 8 and a call on size of n by 8. The same will happen with this C into n by 4 and plus time taken by a call on n by 8 and time taken by a call on n by 8 and n by 8. C into n by 4, right? So we this C into n by 4 is occurring 4 times. So this can be written as C into n by 4 into 4, which is again equal to C into n. So similarly, at this level it is Cn. At this level also it is Cn by 2 into 2, which is Cn, again Cn, again Cn. Here also you will get C into n. So, now the question is how deep we could go, right? This is n, this is n by 2, n by 4, n by 8. How deep we'll go? We'll go till a point where this, right? Better thing to write is n by 2 raised to the power k, because we can see that this is, you can say n by 2 raised to the power 0, n by 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3. So n by 2 raised to the power k will be equal to 1. At the leaf level, at the leaf n by 2 raised to the power k, this should be equal to 1. To make a space on the board, I rubbed that algorithm which I already wrote. It was not a complete algorithm, but you can scroll back to see that, or if you have made a note, you can also, if you have made a note, you can turn the pages in your note to see that. So at t is equal to, at input size, when n is less than or equal to 1, when n is less than or equal to 1, it is supposed to return 1. So, yeah, okay, I have written it over here. So T1 is equal to C, which we can say that T of 1 is equal to theta of 1. So here we can say that n is equal to 2 raised to the power k. So we have to find the value of k over here, because you will use this, because what we need the number of levels in our tree. So n is equal to 2 raised to the power k. We can take log both side. So log of n is equal to log of 2 raised to the power k. Now this can be written as log of k into log of 2 base 2. Log of 2 base 2 is 1. Okay. So we can say that k is equal to log of n. Okay. K is equal to log of n. So what it means that at our leaf level we will have something like this: T n upon 2 raised to the power k, where k is equal to log of n. So let us see, and at each step the time taken is c into n, c into n, c into n, c into n. So at this step also the time taken will be c into n, okay, because this is c and there will be n number of leaves over here. So c into n. Now let me try to solve this. So here we have 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3 and 2 raised to the power k. So so how many times you have this c into n? We have to count the number of times this c into n is occurring. So how many times the c into n is occurring? C into n is occurring c into n plus this is log n from here to here, right? We have log n number of steps and this is one more step. So c into n plus log of n into c into n, right? We can write this as c into n to 1 plus log of n. Okay, you can make this parenthesis over here. Okay, c into n into 1 plus log of n. Now because we are doing asymptotic analysis, and I have already told you that in asymptotic analysis we could be a little sloppy. We could approximate things because our ultimate purpose is being able to compare the runtime of algorithms. So c into n into 1 plus log n. We can ignore this 1 over here. So we can write it as c into n into log of n. C into n into log of n. So this can be written as theta of n log n. N into log n. This can be written as theta of n log n. So here I have used the recurrence tree for finding a solution to this recurrence equation. I hope this this has contributed to making it clear to you that how can you use recurrence trees for solving recurrence relations.